Hello everyone. Today we are going to discuss what are computational errors, what is relative and absolute error, what is error propagation. In our last class we have done floating point representation of the numbers. So let's begin. A friendly reminder, since this is the first time I am doing such kind of video tutorial, so if I make any mistake, pardon me for that. I will try to rectify it. One more thing, this particular video is only for AAC students, that too for 2020 batch. So if you're not an AAC student, this video will not be of great help to you. So what do you understand by roots of an equation? Now before that we must understand what is an equation. So let's say this is an let's take one equation, x cube plus 4x plus 3 is equals to sine x. Now what do I mean by root? Root is that particular value of x for which my right hand side will be equal to my left hand side. So this particular right hand side, it will be equal to my left hand side. So the values for x for which I am going to have such kind of condition is called the root. Now what if I take this value which is present in the left hand side, so in the right hand side, and I take it to the left hand side. So I take everything which is present on my right hand side to the left hand side and I make it in the form of f of x is equals to 0. If this is the form, then what do I mean by root? What do I mean by root is that for a particular value of x, this entire value should be equal to 0. Now let's see it in a different manner. So let's see this equation. So f of x is equals to, so f of x is equals to 0. So what do I mean is that if for those values of x for which I will be having this entire equation, this entire parameter, these values equal to 0 are my roots. Now let me represent this as y. So y is equals to f of x. So let's consider this for the time being. Y is equals to f of x. Let's consider this. Now there are two variables. One is x. So there are two parameters. One is x and another is y. So let's plot them. Let us assume that this is my x and let me assume that this is my y. And this particular function, that f of x, let me assume it to be this way. Some random function f of x. So this is approximated random graph. It may look something like this also, it doesn't matter. It can have any shape, any kind, that will depend upon the equation. Now what do I mean by root? Root is this particular value, this value of x. Why? Because at this particular value of this value, at this particular value of x, my y is equals to 0. And what is y? Y is equals to f of x. So for that value of x for which I am having y is equals to 0, that is my root. All the numerical method solution which we will be seeing, more or less what they happen is that in the iterative process, when initially we take a guess, for that particular the guessed root that I consider, that will be either in this region or in this region. It will be either in this region or in this region. So that will be my initial guess. Then again when I iterate, then I will find another value, then again I will find another value, and in this way it will either converge to this particular point or it will diverge. If it diverges, then we will never get a particular value, we will never get a solution to that equation. So any equation for any iteration that for which my values are diverging from this particular region is not going to give me a result. But if it converges, in that case I will be able to get my results. So how we do that, we will be seeing that in our following classes. So let's move on. So I believe you have understood. So f of x is equals to 0. This is my equation, and what do I mean by roots is, but these roots, my equation, it can have no roots, it can have finite roots, it can have infinite roots, it can have real roots, it can have complex root. This will depend upon the equation. Let's move on to the next one. Now in order to solve any kind of equation, there are two methods. One is the direct method. Direct method is, suppose I give you 4x is equals to 8. So what is x? Suppose I give you 4x is equals to 8. So what is x? You can easily tell that x is equals to 2. So these such kind of simple direct methods where we can directly find. For example, I ask you to find out x square plus 2x plus 1 is equals to 0. So what is the value of x? You can easily calculate and tell me that x is equals to minus 1 minus 1, isn't it? So those are the direct methods. So these methods give you the exact value. Okay. There might be some errors. I mean, if you have not modulated, see, you must understand these equations, this particular equation. How do I get these equations? These mathematical equations are the more are in the real life, they are extracted from the physical real life conditions. Those, okay, we will see later on. Let's not burden you with all the information right now. Basically, you must understand that these particular equations, how have I derived this equation? I have derived these equations from any physical phenomenon. So we have modeled a physical phenomena. We have extracted the mathematical modulation of the physical phenomena, and we have derived the mathematical equations. So that is how we get equations. The next method of solving an equation is the iterative method. In iterative method, what happens is that initially we start with one or two guesses, and then we move on with the iteration. Iterations is the consecutive repetition of the methods, and in this way we come to the concluding value. Now, what are numerical methods and what do we require? Numerical methods are the methods by which we are going to solve the problems. Now, these numerical methods, the data that will be given to the numerical methods will be either in the tabulation form, or it can be in the graphical form, or it can be a figure. So if it is a figure, if it is graphical, if it is a data, it doesn't matter. I have my data, I can take this data, I have the mathematical model, I'm going to put those data to the mathematical model, and I'm going to get the result. Oh, I will either get the result or I will not get the result. If it converges, I will get the result. If it diverges, I will not get the result. What is the aim? The aim of the numerical method is therefore to provide systematic methods of solving the problem. So I am going to take the help of my digital computers in order to solve my methods. Now, what are the steps involved? Steps is that initially we will start with an initial data. It can be a made up random data is equals, for example, I can start from 0, I can start from 1, I can start from 2, or if I have some predefined conditions known, in that case I will be considering that. Then I will be using high-end computers in order to process those data, and after that I'm going to use those data on my algorithm and I'm going to obtain the results. Now these data, these values which I'm getting from the computer model, now they are not the exact values. I mean, they are the approximated ones. Why? Because every computer, no matter how scientific, how costly, how well defined computer you have, it will still have a limitation. In around, suppose when in 2009 and 10, the computers, they were 32-bit computers. Nowadays all the computers are 64-bit computers. So 64 bits means they can process that many bits of information at a single go, isn't it? So then that too also we have limitations. What if the data that needs to be processed is 512? In that case, can it handle? We can do parallel computation, but that's a different idea. A single computer cannot do that, isn't it? So that is one thing you need to consider. The values which I'm getting from the digital numerical methods, pipeline digital methods, those values are approximated values. So I am going to get the errors. So today's discussion will be on those errors only. Okay, let's move on to my notes. Remember, in the floating point representations, I have told you that I have such kind of fixed registers. I mean, we have, see, in a computer, the informations are stored in zeros and ones. Every bit, every information stored in 0 and 1s, and this ones register, this one particular bit, it can store in either 1 or either 0. It will have a limitation. Suppose I have such kind of 5 bits system. In that case, it can store from 0000 to 99 maximum. I mean, that many values it can store, isn't it? Now let's see an example. I have a value 123.456. Now suppose I round it off to 123.46. Why it is 6? Because it is 5 and this is greater than 5, so it will become 6. I believe you know that. So what is the error? The error is the output minus the input, so that's the error. I have taken the modulation, so I'm getting a positive error. What is the relative error? This is the relative error. It's this true error divided by the actual value, so that's the relative error. Suppose I take another value which is 12.345 and I'll round it up to 2 decimal places. That's 12.34, isn't it? Now over here, why haven't I changed it to 5? Because this is 5 and this is an even number, so it will not change. This is the rounding off rule. Over here also, output minus input is this, since it is a modulus. Now if you see these two examples, there is one conclusion that you can draw. For such kind of fixed registers, here I had a number of 1, 2, 3 and the relative error was 0.0032%. Over here I had a number 12.34 and the relative error is 0.04%. So the number increases and the relative error decreases in such kind of fixed registers. You can see it was 123, it is 12. So as the number has increased, the relative error has decreased, because over here it is 0.040, over here it is 0.002, so decrease. So the number increases, the relative error decreases. For whom? For the fixed registers. Now in what is a floating point registers, we have already discussed the floating point registers, isn't it? So over there what happens is that we can represent a very large value or very small value in such forms, where we are going to consider that my system is going to have an exponential part and going to have a mantissa part. Also I have a sine part. This first bit is the sine bit. After that we have the values, and at the end we are going to have the exponential part. Now this base, we will not be considering the base because we know that it is going to have the base. So for that there is no point in presenting the base, since we know that it is there. Now if I use a floating point registers over there, the same particular example which you have seen over in the last, we will find that as the number increases, the relative error also increases. So this is one conclusion that we can draw. Whether it is helpful or not, we will find out later on. Okay, one point you need to understand: most computer languages use floating point arithmetics. Every number is represented using a fixed binary. Digits are called bits. As I have told you, we are going to use computers to solve numerical methods. So we must understand what my computer understands. My computer can only understand binary numbers, isn't it? So it will be either 0 or it will be either 1. So on a base of 10, this is how we represent in a 4-bit system. 1 is represented as 0001, 10 is represented as 1010. I believe every one of you know that. The rules of binary addition you also know: 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0 with a carry of 1. So that is one thing. This is the conversion of binary, decimal and hexadecimal. So in hexadecimal, after 9 we have A, B, C, D. So that is one thing every one of you know. This is a practice problem. I will ask you to solve this and send me. I will be providing you a particular link. I will be having a shared folder. Over there you are going to submit this session. Now I have told you that my computer is going to introduce errors. So what are the sources of error? Now there can be various sources of error. These are the important ones. One is the modulation error, what is the blunder and mistake, one is machine representation arithmetic error, and mathematical approximation error. So what is a modeling error? As I have told you, those physical phenomena will be modeled in mathematical modeling. Mathematical modeling will be done on those. While doing that mathematical modeling, we knowingly or unknowingly we will be introducing certain errors. Those are the physical errors. These errors, these conversion errors, because see, all the physical phenomena cannot be accurately modeled, so we have to take approximations, and because we are taking approximations, that is going to introduce errors. So anytime we introduce approximations, we are going to introduce errors. Then there can also happen a blunder. Mistakes can happen at every stage. You forgot to mention this particular decimal point. You forgot to mention the units. The units was, suppose there was a unit of centimeter and by mistake you wrote millimeter. So those blunders can also happen. Mistakes can also happen while programming. There might be a programmatical error of so these things can be taken care of. These blunders and mistakes can be taken care of by paying more attention while doing the things. But this modeling error, it can be minimized, but it cannot be. You cannot make a system completely modeling error free. I mean, that's not possible. I mean, there will be some sort of error that will be there. Okay. Then we have machine representation arithmetic error. This is also present. Why? Because we are going to use a floating point representations. My system is going to do some kind of truncation or rounding off. So those are going to introduce errors. Then we have mathematical approximation error also. As I have told you, these truncation errors and those things are going to introduce errors. Now, what is accuracy and precision? Now, you must understand accuracy refers to how closely a computed value or measure. Suppose I have my final answer is 5. How many times I can hit a value close to 5? For example, in this particular example, let me assume that this red is the value. So suppose my first is over here, second is over here, third is over here. If these threes are over here, then I can say that this is accurate. Okay. Now what about precision? Suppose the first value is over here, the second value is over here, the third value is over here. In this case, what has happened is that though the actual answer was red, but my values which I got are over here. Now this is highly precise system. Why? Because precision has occurred, but accuracy is not occurred, because I was hoping to get red, but I did not get that. What I got is that I get multiple number of blues. So precision is that how many times you do the same thing. I mean, how many times you get the same result. That's precision. And accuracy is that how many times, how close you are to the actual value. So that's one way of representing. I believe this can explain you better. As you can see, in this way the accuracy increases. Obviously, see, this is more accurate. It was, as we go in this way, more accurate results. And now over here precision increases. See, these values are clubbed up at this point, so this is more having more precisions. Now, as I told you, what is the exact value? The exact value will be the approximate value plus the errors. So we must understand error, we must calculate error so that we can minimize the error. Only when we know what we are dealing with, we can minimize it, isn't it? So to get the exact value, we need the errors. So there can be absolute error or relative error, there can be inherent error, there can be rounding of error, there can be truncated error. These are the most common computational errors. So let's move on to the next. Let's see this particular thing. Over here, what do I have? This e to the power x, it can be represented in this manner: 1 plus x square plus modulus of 2 plus x cubed by modulus of 3 plus in this manner, isn't it? So what is the true value? I mean, if I consider to 6 decimal place, then this is the true value, isn't it? How I have got this? See, I am finding e to the power 1. So over x, I will be putting 1. So it is 1 plus 1 square by 2 factorial plus 1 cube by 3 factorial. This way I am going to put this and I am going to get this true value. Now suppose I approximate it up to this point only, then what will I have? 1 plus 1, so I'm going to have it 2. So the true value was 2.718282 and the value approximate error is 2. So what is the absolute error? This is the absolute error. True value minus the absolute value. And what is the relative error? True minus approximate divided by the true value. So that's into 100%. That's the relative error. Percentage relative error. Now, suppose I take up to these three part, the first three. I'm considering the first three. Then what I will have? I will have 1 plus 1 plus 1 by 2. It's 2 factorial, so it's 2 into 1. It's 2 only. So over here I'm going 2.5. Isn't it? Now I consider the four of them. Then I will have 1 plus 1 plus 1 by 2 plus 1 by 3 factorial, which is basically 3 into 2, which is 6. So as the number of terms are increasing, I am getting a value which is closer to the true value. So as I am increasing the number of terms, I am getting the value close to the true value. So now it will depend upon your requirement, how accurate you need the result. If you need more accurate result, you are going to consider more number of values. But the problem is that the more values you take, the more computational steps that will be required, the more amount of time will be required. So resource versus accuracy is something which you need to consider always. So in truncation, what happens is that we are going to truncate at particular value. Suppose over here what I did is I truncated at this value. I did not approximate it, I did not do anything, I just truncated. I just said no, I'm going to take only consider this two value only. So that's a truncation. And rounding off, what happens is that suppose it is over here 8 2, no? So when I round it off, since it is less than 5, so it will remain as 8 only. Now if it was 5, in that case also it would have remained 8. Why? Because it is an even number. But if it was 6, this particular 2, if it was 6, in that case I would have made it 9. So that's how we're going to round it off. So truncation and rounding are the two most common errors that are introduced. This we have already discussed in the floating point representation. The first one is the sign bit. So now what is propagation of error? Now you must understand that suppose I have two values, I have x and y. Now this x and y is also going to have some kind of errors, which is delta x and delta y. So what is this delta x? This delta x is the error for x. And what is this delta y? Delta y is the error for y, isn't it? What is, see, what is the exact value? Exact value is the approximated value plus the error, isn't it? So this is the approximated value, this is the error. Only then I will get a true value, which is my x. Now when they are added, when x and y are added, the errors are also added. When the values are subtracted, then also the errors are added. So this is something which you need to pay attention to, isn't it? What happened? Okay, only for reference purpose, always study from standard books. Okay, whenever I am subtracting two values, but I have to add the errors. What if we do multiplication of two values? In that case, this is how we are going to consider the errors. Delta x by x plus delta y by y. In case of division also, this is falls under propagation of error. We will discuss this later on in a more detailed manner. This is just an introduction of the terms. See, I will be taking a particular approach. What will I do is that in the initial stages I'm going to explain you briefly all the terms, everything I'm going to explain you briefly. Once you have a complete idea of everything, and the entire syllabus will be a sort of complete, only then I will move into more in-depth analysis. Because as you know, we are taking the classes online, so there are certain limitations because I do not have a digital pen to write everything. So those are the limitations that I have right now. We will work it out initially. This is how we're going to move on. Okay. So I believe you have understood what is the propagation of error. To pay attention that even if it is x minus 1, when I'm subtracting the values, I am still adding the errors. But in the case of multiplication and division, it is something of this sort. But this is important. So that's absolute error and relative error. I believe you have already seen. If x is the exact value, x is the approximate value, then what is absolute error? Obviously, approximate exact value minus approximated value, and relative error is exact value minus approximate value by the exact value. That's the percentage. What is the inherent errors? Inherent errors are the error that is pre-exists in the problem. I mean, for example, while considering the data which we consider, the initial data which we consider, those were faulty data. So that is an inherent problem. The computer which you're taking, suppose I need to process more than 32 bit of data at a single time, but the operating system and the machine that I have is a 32-bit system. Then that is a problem. There's an inherent problem, something which we cannot deal with, which we cannot minimize. So you must understand that inherent errors cannot be completely eliminated, but it can be minimized by using a better data or using a high precision computers, isn't it? If the data required needs to be more than 32-bit, in that case I will consider 64-bit operating system and a machine. The data which I'm taking, if I need to take it from a reliable sources, isn't it? So these are the things which we can do to in order to reduce the inherent error, but we cannot minimize it completely. Then what we have, let's see over here. Suppose this is the value of pi, isn't it? This is the value of pi, and I'm going to consider the first 6 decimal places. So what I have over here is that I'm asking you to find the relative error by chopping and by rounding up. There are two ways, isn't it? So in chopping, what happens is that, as I've told you, since I'm going to take 5 decimal digits, so these are the first 5, 1, 2, 3, 4, 5, isn't it? These are the first 5. So as you can see over here, in chopping, I directly chop it. Directly I cut it at this point, and then I'm calculating the error. So in the relative, in rounding off, what I'm doing is that since the value over here, this particular value, this value is 9, which is greater than 5, and this is an odd number, so I have replaced it with 6. So this is rounding off. So that's how we find out, isn't it? Now let's see one more example. Given two numbers, I have this number which is a is equals to 8.890 and divided by 3, and b over here. Now we need to calculate a minus b using the floating point representation, meaning I'm going to use the scientific notation. I'm going to consider this divided by 3 also with 3 significant digits. 3 significant digits means to these 3 places. Over here is 3 only, but over here it was 5. I'm going to consider only the first 3. So first in chopping, what we are going to do, in chopping we are directly going to cut it at this point. Directly at this point we are going to cut it. So I have this over here. And b is, so it's of 3 decimal places only because it was mentioned over here. So what will I have is, let's see whether it is true or not. 8.890 minus 8.887. So you see it's 0.03. When I multiply 10 to the power 3, I am going to get 3, isn't it? When I'm going to so I'm going to get 3 only. Okay. Now let's do the next one. In the next one, what do I have? I have rounding off. In rounding off, what I'm going to do, see this particular value, this is 9. This is 9, isn't it? If it is, and what I'm going to do is I'm going to replace this with 1. So I have rounded off. So if I round it off, then what will happen? Let's see. It's 8.891 minus 8.887. So it's 8.891 minus 8.887. What do I have? I have 4. When I multiply with 10 to the power 3, I have 4, isn't it? So when I chopped off, I got 3. When I rounded off, I got 4. But what is the exact result? So if I find the exact values from here, then I will have to multiply 10 to the 3 over here. So what will I have is 8.890.9 minus 8.887. So it's 3.9. So the exact value was 3.9, but when I chopped off, I got the value 3. When I rounded off, I got 4. So these are the these are the approximated values, isn't it? Yes. Truncation errors are defined as the error that results from approximating, dynamic truncating. So that's something. And rounded off, you understood what is rounded off. What are model errors? Model errors are related to bias. I mean, while modeling, there will be error introduced. Suppose while modeling the temperature which we consider the constant temperature, but obviously in physical condition constant temperature is not possible. Every time the temperature changes, the wind velocity changes, and the current direction, the current intensity changes, the flux changes, isn't it? So there are so many. Suppose you are trying to model a particular system and suddenly a phone call came. Now this phone call is going to induce electromagnetic waves, so that may be introduced into your system as a noise. So those modeling errors, can be considered. So, so for today, up to this much. In the next class, we will move on with the basic, the first real chapter, which is how to solve the numericals and this transcendental equations, method of bisection, how we're going to use it. So that's for next chapter. Thank you.